So post your questions on chat if you can, if you have any.
There we go. Okay, we all set? Ready to get started?
Yes, James, you're on. Yeah, thank you.
Full people here today. How many are in the chat? I can't see the
4 or 5.
5. Okay, there's about 8 total. Okay. So I don't have to actually see. I was just kind of curious how the audience is here. So yeah, so welcome to Fundamentals of Light Trapping. I've been giving this lecture once a year, like the last 10 years, ever since I finished my PhD here. So I graduated here from the university in 2011, and my dissertation was on light trapping in thin film solar cells. I did a lot of simulation and modeling for that. So kind of became the resident expert on how to make light stick in solar cell. And so I've just been kind of giving this lecture every year ever since. And it's kind of neat to see some of the changes that have occurred over the last 10 years, which we'll kind of talk about as we go through. So my background is, I guess I'm an engineer / instructor. So I'm not a professor per se, but I'm a staff engineer instructor person. And I'll actually be leaving in January to go work at L3. So this is my last semester here. So lucky for you guys to get my final lecture on this. My specialty, and I guess I should also ask, you can hear me, right? Is this the microphone I should be concentrating on? Just to check with the audience online, Rajesh. I'm assuming you can hear me well, right? I guess he's muted. So I guess someone will say something if they can't hear me. So my background is applied electromagnetics. So I like just playing with Maxwell's equations and modeling things, doing numerical methods, empirical techniques, simulation, and just modeling stuff. Doing math is really what I do well. So this lecture is about light trapping. So just a quick sort of philosophical foundation of what the heck does that even mean. So you imagine something floating in space like that blue droplet there. It could be like a raindrop, say, and it's being illuminated by light. Obviously, some of that light is going to bounce away. By the way, can I use my pointer here? Just out of curiosity, do the online people, can they see the pointer if I do this sort of thing? Okay, so they're good. I can point to stuff then. So you see some light will kind of bounce off and scatter away. Some light might transmit through and bounce around and eventually be absorbed. Another light still might just fall away out the backside. But we care about the absorbing bits. So what you would define is, say, there's some cross-sectional area of this physical object and it's being illuminated by light. And you take the fraction of the light that is being absorbed inside of it relative to the total energy striking it. That is what we call light trapping efficiency, or you can call that an absorption factor. So some basic applications, why this sort of concept might be important. So one of the quintessential is the good old stealth bomber there. You're illuminating it with radar waves, and you want to have that magical radar absorbing paint that they put on these airplanes to minimize the echo back towards the sender. So that's kind of a light trapping application. Obviously, we're here for optics for energy, so solar cells, photovoltaics is kind of the quintessential application for a class like this. But you can also think of things like an anechoic chamber, which we have one over in the Merrill building. You have light that, say, bounces off your antenna here, or is being radiated, and it will strike the walls, and you don't want the energy to bounce off the walls and corrupt your measurement. So those are called echoes. It's a not echoing chamber, an anechoic chamber, and just the science of getting this magical pyramid foam stuff to absorb light is like a huge field of science unto itself. Right? So we're going to talk about solar panels and solar energy. So this is a really fun graphic which shows just how much light is striking the United States. How much energy is there available to us to harvest from the sun and put into the grid? So this is from NREL. So if you ever do any sort of photovoltaic kind of research, NREL will be your best friends. They're the National Renewable Energy Laboratories. So they're really good at producing kind of nice national scale infographics like this to help guide policy and research. You notice the units here are kilowatt hours per square meter per day. So you imagine, say you're out here in Arizona, I have a 1 square meter aperture. How much energy would be striking that aperture over the course of a single day? And then if I average that over, say, a year, it's upwards of, say, 6 to 7 kilowatt hours per square meter. Right? And of course, up in Alaska, it's really terrible. It's like half that. And you can see there's a trend as you go further and further north. It gets a little weaker. It looks like they're even accounting for weather, because you see how up here by the coast, where it's all cloudy and rainy, there's this little dead zone here. So I'm assuming that's because of cloud and rain, that kind of thing. So it's a pretty neat graphic. So I used to always begin this lecture by saying, look, here is a solar farm out in a desert somewhere, and here is a giant desert with nothing better to do than give us free energy for the entire country. Why are we not flooding the desert with solar panels and providing ourselves with energy for the entire country? And 10 years ago, there were all these horrible economic hurdles to that. But now it's actually kind of turning around. So this is a really fun graphic I found the other day. This is new new electrical grid infrastructure being installed, generating capacity. So we have all these power plants around the country generating energy, and every year people are building homes and businesses that need more energy, so the grid has to expand in order to accommodate that increase in demand. So this is the additional capacity being generated, the capacity additions, and you see it's about 56% solar from 2021. So this is probably kind of a projection. It's not, the year's not over yet, but it's pretty close. See, it's almost 40%, 37% on wind, a little bit extra on natural gas, and there's that tiny little sliver of other. So we're almost at a point where all the new electrical infrastructure being built in the United States is totally carbon neutral, renewable energy here. So we're not quite, but there's a milestone that is coming. And it's kind of fun to look at this graph, because I remember giving these exact same kind of lectures 10 years ago, say 2011, 2012. You see solar was barely 8 or 9%. Wind is like 30, 40. Natural gas and coal are making up the rest. And it's just neat to see 10 years gone by, that trend is totally probably just going to keep on going that way into the foreseeable future. So that was cool. I didn't realize that. Part of what's really fueling that, of course, is economics. As we manufacture more and more solar cells every day, the process of manufacturing them gets easier and easier, and you get all these wonderful economy of scales and standardizations and et cetera, so that as the sheer volume of photovoltaic installation grows, the cost per unit goes down. And so this is kind of like its own pseudo Moore's law trend going from the 1970s down to not quite today. I wasn't able to find an up-to-date graph of this for 2021, but you can see the trend is pretty rock solid there. There's another just fun graphic showing they call it the turnkey pricing. So I'm not 100% sure what that means. I think it means when you sit down with a contractor and write them a check, and it's not just the photovoltaics, there's like the parts and labor involved in installing this stuff and then integrating it into the grid. So that tends to add a lot of extra cost as well. So if you are a big commercial person and you do a large order, you can almost get to a little under $1 per watt, which is kind of regarded as the milestone where you are better than coal and natural gas if you are that cheap. Obviously, residential is not quite so great. You're upwards about $3 per watt. Impressive. Just those trends are just down and down and down. That's pretty neat. Okay, so let's talk about the basic physics and anatomy of a solar cell. So a solar cell begins with a chunk of semiconductor, and you dope it to have an N-type and a P-type with a junction here, so a PN junction. There you have a top metal contact, which might be aluminum, silver, say, bottom contact, and then you shine light on it. So what happens is a photon, as it propagates through this material, has some probability that it will eventually slam into an electron and excite it into an excited state, leaving behind the hole. So you get the electron hole pair, and then they just, through the sheer power of diffusion, will meander through the PN junction to the top and bottom contact, and you get usable energy that can come out of that. Cool. So the first question is, what do you make a solar cell out of? And the answer to that 10 years ago was a huge debate over what should we be making these solar cells out of. But silicon has completely solved that question for a number of reasons. So, for example, silicon is very much abundant in the Earth's crust. If you were to just go outside and grab a clump of dirt, something on the scale of like 40% of the atoms in your hand will be silicon. So it's wildly abundant in the Earth's crust. We're never going to run out. And believe it or not, there are other kind of photovoltaic materials that do very well, but they're just made out of rare materials. So I think 10 years ago, there was a company called First Solar. They made a solar cell out of cadmium telluride. So problem, of course, there just isn't enough cadmium and tellurium on the planet to really satisfy the sheer volume of solar cells we would need. So that abundance in the crust turned out to be very toxicity is another issue, because of course, making billions of these things, eventually they're going to need to be recycled or thrown into a landfill at some point. So silicon is pretty non-toxic in terms of, like, if you get into the water supply, it's not going to leach out and cause trouble. Whereas something like cadmium telluride, the cadmium is a heavy metal that is potentially toxic. So what do you do? What do you do with the disposal of all this stuff down the road is a big factor that we have to be concerned with. And as luck would have it, we have 50 plus years of this huge semiconductor industry doing magical things with silicon. So we're already just good at processing silicon to begin with. And as luck would further have it, the band gap for silicon is kind of right about what you would want it to be for an optimal solar cell, given the star that we are in orbit around. So we'll kind of talk about that issue in a little bit. But just the band gap itself has sort of issues with the optimal efficiency. Okay, so let's kind of start walking through the chain of turning photons into electricity. So what you do is you imagine you're floating out in space in Earth orbit, and you get a big photometer, spectrometer, and you just point it at the sun, and you wait a year, you just average everything you see. And so obviously, like, the Earth will kind of drift a little farther away and closer because it's not perfectly circular orbit. The sun will have like its 11-year cycles where it goes up and down by a few percent, and you get sunspots, blah, blah, blah. Average all of that out for a year, and you basically get that black curve. It's called the air mass zero solar spectral standard. And for kicks and giggles, I threw on a black body radiation spectrum just to kind of show that's a nice indirect way to get a sense of how hot the sun is at the surface there. So you look at the units, you notice it's watts per square meter per nanometer. So what that means is not every photon has the same amount of energy. Some different wavelengths carry different energy with them. And this is sort of the spectral distribution. So if you take the area under this curve, you then get watts per square meter. So then you imagine a 1 square meter aperture just collecting area. So you would multiply it by that area, and what you would get is power. Okay, so usually we leave it in terms of power density. It is about 1.366 kilowatts per square meter is sort of the take home of energy. The sun is just shining upon us at every square meter per day, right? Or every second of every square meter throughout the year on average. So that sounds great and all, but it's not really the whole story. We here on Earth we have an atmosphere between us and the sun. So if you imagine looking straight up, there is exactly one atmosphere of molecules, oxygen and nitrogen and water vapor, and they're scattering light and they're absorbing orbit. So you see some of these little absorption lines going on here. I think a lot of that is like oxygen and water vapor. Find somebody with a specialty in spectroscopy could probably tell you exactly what these little dips are and what they correspond to. You know, someone would say that little line there is, you know, the twisty motion of the N2 molecule, say, and this one over here would be, you know, the back and forth of O2. Or maybe this one over here is the ozone layer, you know, that kind of stuff, right? And then of course there's the actual scattering from, say, aerosols and that kind of thing in the air. So you get slightly less energy than you would if you're in space. Now, the story is actually slightly more complicated. So that would be called an air mass 1 spectrum, but we are on the continental United States, which means the sun is not really directly overhead. It's kind of mostly at an angle, right? And the Earth is tilted. So you imagine averaging all of that nonsense together, and you have roughly on average 1.5 atmospheres of air that light has to travel through before it reaches us here on the ground. So that's why it's called the air mass 1.5 solar spectral reference. And it's kind of regarded as a hand wavy way of saying this is about on average what the continental United States gets if you were to collect area across or to collect sunlight in an area. And you can actually buy like light bulbs that produce this spectrum and use them to more or less quantify the efficiency of a given solar cell, right? Because if I come out and I sell a solar cell to you, I need some way to tell you how good it is, right? But you got to be careful because somebody in Maine is going to get different results from somebody in Texas when they install this on their home. So this is a sort of universal reference that everyone has agreed to measure solar cell performance. So if it does better on this spectrum, it will do better wherever you install it. So it's a way of comparing solar cells against each other by saying this is a 25% efficient cell, this one's 18, that kind of thing. They're usually measured against this reference. And so by a wonderful happenstance, it looks like we also chose this just to round off to exactly 1 kilowatt per square meter. So I think there's a little motivation there to make things nice and easy. So you can think that as on average, we in the United States get about 1 kilowatt of energy per square meter average across the year. So now we're gonna complicate things a bit because we don't. The raw energy is not really useful in a sense. You can capture a photon, but that doesn't necessarily mean you're going to extract all of the energy out of it. So since we care about light trapping and not necessarily the quantum efficiency of converting that to electricity, it actually is much more useful to think about light trapping in terms of capturing photons rather than capturing energy. And the main reason for that is the band gap, for example, of silicon, right? Silicon has a band gap of about 1120 nanometers. And what that means is all of these longer wavelength photons mean nothing to us. They physically don't have enough energy to excite an electron-hole pair. Therefore, for all practical purposes, they just might as well die. So I'm going to erase them from the spectrum, right? So you notice that immediately just says, all things being equal, 800 watts per square meter is the best I could ever hope to collect using a silicon solar cell. But the story is also more complicated than that because if I excite an electron with energy greater than the band gap, I can't really keep that difference. It just sort of immediately settles back down to the band gap and the rest of that energy is wasted as heat. So even if I trap the photon, I won't necessarily get a perfect transfer of the energy here. So you notice the units have been converted into photons per second per square meter. So if I integrate all this, I'll get so many photons per second landing on, and I can trap them or not. And we're not going to really fuss too much about the quantum efficiency aspect of this. We just want to trap the light. So if you take like a photovoltaics class, they'll go through a big derivation of just what is the absolute maximum efficiency you could theoretically get out of a solar cell with a given band gap. And given that I have to now do like the Thevenin equivalent circuit of transferring it to flow, that kind of stuff, there's some weird thermodynamics issues and then the recombination loss. So it turns out the thermodynamic limit for efficiency of a solar cell is about 32%. So again, we're not going to focus too much on efficiency per se, but the light trapping is going to be a big part of it. So when you account for the band gap stuff, you get about 500 watts per square meter, and then you account for some of the other weird stuff going on. 32%. So this is the absolute maximum efficiency that nature will give you for a silicon solar cell, given the spectrum from our sun. Okay, so that's an important idea, is the spectrum itself will change the efficiency of your solar cell. So that's called the Shockley-Queisser limit. Fun fact, but that's a good little benchmark to give some perspective on how this stuff works. So how do you make a high efficiency solar cell? This is a fun graphic. In 1999, this paper that I pulled this from was the world record holder for silicon solar cell efficiency produced by a laboratory. And they were able to get about 25%. So who knows how much that has changed in the last 20 years. I would be very surprised if they got more than, say, 26 or 27. But that's just kind of show that when somebody really puts their mind to it, that's about as good as you can get relative to the absolute limits given by nature, say. And you'll notice that the typical thickness of this substrate here, you see the PN junction is very thin, but this whole guy here is about 400 a 0.5 millimeter. And you have to put it together in these little cells that kind of get soldered together. So that's why you see these little 100 square centimeter cells on a typical solar panel. So this was built in a laboratory. This guy here, I just did a little research, high efficiency solar cell shopping, click. And it turns out you can buy off the shelf about 22.5, 23% efficiency. It's $2, $2.50 per watt. So fun fact, 10 years ago, no way you could get something like this. Now this is just being installed in huge installations mainstream. I don't think you can quite get this on Amazon. This was more like an industrial manufacturer, but I just thought that was cool. It's basically an off-the-shelf panel you can get, and that they're almost right there what you could get in a laboratory value there. So we're going to focus strictly on the light trapping. We're just going to assume all the other stuff is perfectly optimized. You still have to capture the light. So how do I trap light? Well, a good way is to just say I'm shining light on it. Where does the light just go? So the first thing you'll get is, of course, light comes in. Some of it will bounce off the surface here. So you get these surface reflections. Some of it might go all the way down to the back contact and fly out the surface again and never run into anything. And then you have like the little metal contacts at the top, those little metallic fingers that interlace. And they will block light too. So you can see how there's just physical things that are going to get in the way of your ability to reach that perfect limit. But some of this you can handle pretty well. Like, for example, you can minimize those surface contacts, right? That's why when you look at a solar cell, those little metal traces are teeny tiny and they're very, very sparse and spaced apart from each other. You can put an anti-reflective coating on it. So usually silicon nitride is something for that'll work pretty well. But you still have that back and forth reflection here. So what I can do is I can maybe make my solar cell very thick. That's why that high efficiency one was 400 microns thickness. So that gives you a lot of opportunity for light to go down and eventually run into something. But sidebar, don't make it too thick. Otherwise, your electron and your hole will just recombine again and have nowhere to go. So you can see there's some inherent trade-offs between your light trapping and your thermal efficiency. So here's an interesting little graph. So this shows the absorption length as a function of frequency or wavelength for silicon and gallium arsenide. So gallium arsenide is a pretty efficient direct band gap semiconductor. So you see it has a very small absorption length. You see how this is powers of 10 microns. So here is 1 micron, 10 microns, say. And one absorption length, think of it as the probability of a photon being captured, or sorry, it is the length required to get a 63% probability of capturing a photon. So a 1 over E kind of decay thing going on there. And you see, because gallium arsenide is a direct band gap semiconductor, it has this nice curve that once you get to the band gap, suddenly shoots off to infinity there, where all of a sudden you're not capturing. Whereas silicon is an indirect band gap. These houses this much smoother profile as you get up towards 11, 20 nanometers. So the band gap is right around here, and you can see how it just kind of shoots off to infinity. So you need many tens, if not hundreds of microns in order to capture these photons that are really close to the band gap. So this has given rise to this notion of, or this is kind of in conflict, I should say, with the notion of a thin film solar cell. Because I guess if we go back a little bit, this used to be a big issue. I don't think it's quite an issue economically anymore, but back in the early 2000s, that lump of silicon here, that 400 microns, is about half the cost of that entire solar panel assembly. Just the raw silicon itself was a huge cost in there. It looks like they've kind of gotten around that problem in the last 15 years or so, but that was a big, big deal, which motivated this idea of thin film solar cells. There's still other advantages to going thin, but the idea is instead of being hundreds of microns thick, you shrink it down to, say, 2 microns. And there's still some interesting advantages to that. First, like instead of growing the silicon, you're kind of printing it almost like a newspaper, and it's flexible. So there's some applications where that flexibility actually gives you a lot of interesting benefits when you go thin like that. So it's very cheap to manufacture. You get that flexibleness going on. But you notice you take a huge hit in your efficiency. So this is something I found on Amazon, a flexible monocrystalline solar panel, 100 watts. You notice it's cheaper, $1.7 per watt. There's even cheaper stuff still. But the efficiency tank is like 1/4 the efficiency when you do this sort of thing. So it's that problem of the decay length, right? So here at 500 nanometers, using the values for silicon, you can see how like 90% of your energy is just absorbed and decayed in that first 2 microns there. But if you're up at say 800 nanometers, still not even that close to the band gap, you barely scratch the surface in that tiny little that thin film there. So yeah, they're cheap, but you take a massive hit on your efficiency and your ability to capture light when you go thin in these solar panels here. So that's where this notion of light trapping is going to come and why we care about it. So this is a great example where just to get a sense of how difficult the problem is, it helps to just do the calculation of the electromagnetic model. You imagine light striking this planar boundary from the top. And I make it 1 micron of silicon with a perfect electric conductor at the end. And you just run the electromagnetic model and ask how much energy is being absorbed in this 1 micron slab of silicon. And you compare it to the actual solar radiation from the sun, right? So the idea is if I had absolutely perfect light trapping, that red curve there should match the dotted black curve here from the sun. And so you notice what you get is if I do a very bare bones light trapping or very bare bones thin film solar cell, I barely get a light trapping efficiency of about 27%. So meaning the ratio of this area to that area is only 27%, and I'm throwing away 3/4 of my energy. And so if you then put that light trapping efficiency onto like the Schottler-Queisler limit, you find that the maximum efficiency I could get from a solar cell is 8%, just a bare bones kind of value like this. So first thing you might want to say is, well, what if I put an anti-reflective coating on? So that gets rid of some of the initial reflections. You see that sort of smooths out all that Fabry-Perot resonance. But even then, my light trapping efficiency is only about 40%, meaning I would only get maybe 13% efficiency, my maximum performance. Right? So you take the Shockley-Queisler limit, then you multiply it by that 40%, and you get about 12%. Right? So that makes us very upset. We really would like to know if we can do better. So there are fun ways to cheat the physics a bit and get better performance. So what you imagine is, here's a solar cell. I'm going to make the bottom contact bumpy, and something immediately jumps out where I have this path length going down and then back is 1 micron down, 1 micron back, so 2 microns. But if I can somehow convince the energy to go sideways, I have essentially infinite depth to propagate through, whole square meters of material in the sideways direction. So if I can somehow just convince light to not go straight up and down, go sideways, I'll get it's called a path length enhancement, right? So instead of going down and back 2 microns, I might get 3 or 4 or 5 or 6, just by the mere virtue of scattering the light and making it bumpy. So let's quantify that and look at that some more. So that gave rise to this notion. It's called the Lambertian limit, or the ergodic limit, or the Jablonovich limit. Some guy named Eli Jablonovich did the calculations for this like in the 90s, I think, and found that the best you could do is, well, we're going to derive it actually in a bit. But in this particular case, you find that you reach almost 80% of your light trapping efficiency if you had this sort of perfect Lambertian scattering of your surface. So light comes in, scatters around, and it just sort of bounces around back and forth. This recycling of scattering at each reflection period. So you notice that implies, hypothetically, a 1 micron film of silicon could almost reach 26% efficiency, which is pretty close to that 32 we saw with the Shockley-Queisler, right? So that's pretty interesting. So we'll talk a little bit about that. So this had this wonderful renaissance, but it was the really fashionable research back in the 2000s. Where people were just cracking their heads on every which way to try and make light bounce around inside of solar cells. So just dozens of papers going all over the place. And that's kind of where I jumped in around 2008. And this thing here was like the greatest thing ever. People thought that if you sprinkle little spheres of gold and silver onto their solar cells, that somehow that was going to make them more efficient. Which is kind of funny because one of the first things you notice is big pieces of metal on top of your solar cell is like the last thing in the world you would ever want. But somehow that got published in there. People were very excited about this. And then just the fact that they're using rare metals like gold and silver, funny to me. But this was big science 15 years ago. And I was neck deep in it doing my PhD here. But you have all these ideas like, you know, surface texturing, little pyramids and things, diffraction gratings, make things bumpy so that light scatters every which way. It's kind of the so on time. We got plenty of time. Okay. So the language of light trapping is kind of interesting. You have this idea of what's called a path length enhancement, right? So it's an interesting question. How do I sort of create a mathematical Platonic ideal of that so that I can sort of talk about that in a sensible way and give it meaning? So I did a bunch of digging, and there was some really obscure textbook I found that gave this idea of what's called a model N slab. And I think it's really neat because it really gives sort of a mathematical formula to this sort of discussion. So you imagine here's air, and here is a slab of material, right? Just a big planar, infinite planar chunk of something with some thickness W here. And the N means no reflection. So we're going to imagine, for whatever reason, there's no reflection happening here. Light comes in, it just enters, it gets absorbed, and then it falls out the other end, right? So we're going to ignore that reflection bit. So then the question would be like, what is the absorption factor, the light trapping efficiency of a system like this? So you notice I throw away the R, I get the absorption is 1 minus T. So these are all normalized to the incident intensity. So think of these as fractions, right? The absorption fraction is 1 minus the transmission fraction. And the transmission then follows a exponential decay, e to the minus alpha W. And so what that implies is you solve for the thickness now. I get this W is -1 over the absorption coefficient times the natural log. So the idea is that if I'm given this absorption factor, I can calculate the width, or if I know the width, I would calculate the absorption. But this creates sort of this ideal scenario in your head where if I have some light trapping solar cell and I know what its absorption fraction is here, I can imagine in my head some equivalent slab of material with some length W here. So I'm going to call this L. So W would be like the actual length. L is what I can imagine is the fictitious equivalent of it. That's called the equivalent path length for absorbing structure, like your solar cell, right? So if I have a solar cell, it could have some real thickness, but light is bouncing around in it, being absorbed. So I would say it is behaving as if it were this model N slab with this much thickness, like 10 microns thick, say. So you would then refer to this idea of a path length enhancement, where you'd have, say, it's a 1 micron thick cell, but it's behaving as if it is 10 microns thick. That's kind of the language people like to use for this. So I kind of like this little thought experiment because it sort of gives a mathematical meaning to these ideas. So the take-home point is, give me an absorption factor A and the attenuation coefficient for that material at this wavelength, and then I will tell you its equivalent path length. So you can do some fun little calculations, right? Here was our initial slab with nothing on it. So imagine light comes down, there's a little reflection here, there's a bunch of bouncing back and forth that happens. So that's called the Fabry-Perot resonance. Sometimes it's all constructively interfering on the reflection. Sometimes it'll destructively interfere, depending on the wavelength, which means your equivalent path length might be very large or very small. And you can actually go through the math and prove that for the maximum absorption, so that would be the destructively interfering case, your equivalent path length of this slab is weighted by the index of refraction. So you notice the factor of 2 represents the path length going down and reflecting back. Then the index of refraction will scale it even more due to the factor. The opposite can actually happen when you get the constructive interference on the reflection. You get a reduction by this index of refraction here, this N. So that's what these curves here represent. So you see the Fabry-Perot resonance here, you can kind of trace the peaks and the valleys. So the valleys there are the 1 over N, then the peaks up here are the multiplied by N. And then you can imagine like an anti-reflective coating here, so there's no resonance effect at all, it just goes down and back. So this 1 micron slab of thickness would behave as if it's just 2 microns thick on that idealized sense, and that's what that blue curve there represents, which is kind of cool. So you can see it gives you this sort of nice intuitive length